All right, let's jump right in. We're going to be talking about a technology that could completely change how we see and measure the world around us. From what's deep inside the Earth to the tiny signals firing in our own brains. This is all about quantum sensing.
But to really wrap your head around it, let's start with a little thought experiment. Picture this. You're in the middle of a massive, roaring crowd, and you need to hear a single tiny whisper from way across the room. I mean, it sounds impossible, right? Just hang on to that idea, because it's the perfect way to understand what's going on here.
So what's the big deal with this technology? Well, we are talking about unlocking a whole new level of perception, the kind of thing that, until now, has basically been science fiction.
And listen, this isn't just some abstract idea. The real-world applications are absolutely staggering. Quantum sensors could give us navigation systems that don't even need GPS. They could help us find new mineral deposits buried deep underground. We could create atomic clocks so precise it's hard to even imagine. And maybe most incredibly, they could detect the super faint magnetic signals from the human brain, which would be a total game changer for medicine.
Okay, so what's the secret sauce here? How on earth do these sensors get this super hearing? The answer is one of the weirdest, coolest, and most powerful ideas in all of physics, quantum entanglement. Everything starts with something called a qubit. You can think of it as the quantum version of a regular computer bit. But, a normal bit is just a 0 or a 1. A qubit, though, can be in what's called a superposition. It can be both a 0 and a 1 at the exact same time. It's weird, I know. But that strange state makes it hypersensitive to the smallest little disturbances in its environment, like a tiny magnetic field.
Now, common sense would tell you, hey, if you want a better measurement, just use more sensors. And, you're not wrong. If you have, say, 100 separate quantum sensors, you definitely get a better, more sensitive reading. But there's a way to do way better than that.
And this is where it gets absolutely nuts. Check this out. If you take those 100 sensors and just let them work on their own, you get a 10 times improvement in sensitivity. That's pretty good, right? But if you link them all together using quantum entanglement, they stop being 100 little sensors. They become one giant, unified super sensor. And the result? A 100-fold improvement.
Yep, you heard that right. 100 times more sensitive. This is how you hear that whisper in the roaring crowd. You get all your listeners to work together so perfectly in sync that they can pull that one tiny signal out of all the noise. That is the incredible power of entanglement.
Of course, it can't be that simple. There's a villain in this story, a constant, nagging enemy that's always trying to ruin the party. And that enemy is noise. Because with quantum stuff, the very thing that makes it so powerful also makes it unbelievably fragile.
So yeah, what's the catch? I mean, if this tech is so amazing, why don't we have these sensors everywhere already?
Well, the catch is what scientists call environmental noise. And that's just a fancy term for any little disturbance from the outside world. Tiny changes in temperature, little vibrations you can't even feel, stray magnetic fields from your phone, it's all noise. This is the roaring crowd that is constantly trying to drown out the whisper you want to hear.
And this gets us to the central paradox, the real tricky part of quantum sensing. Those delicate, spooky links of entanglement that give you the superpower, they're also the system's Achilles heel. They are super sensitive to the signal you want, but they're just as sensitive to all the noise you don't.
So here's how it all falls apart. You start with this beautiful, perfectly entangled system of qubits. But then some random environmental noise hits it. Bam! That noise causes errors, it corrupts and breaks those fragile links between the qubits, and just like that, your 100x advantage is gone. Your super sensor just collapses back into a bunch of regular old sensors.
For the longest time, the only answer people could think of was trying to build a perfect, noise-free bunker for the sensor. But a new research team, which includes scientists from NIST, came up with this brilliant, kind of weird, and totally counterintuitive idea. What if you don't fight the noise? What if you just meet it halfway?
See, the old approach was all about perfection. You had to shield the sensor from every possible bit of noise. But trying to do that in the real world, it's basically impossible, not to mention crazy expensive.
But these researchers had this light bulb moment. They asked, what if, for sensing, you don't actually need to fix every single error? What if good enough is actually way better than a failed attempt at perfect?
As Jacob Lin, one of the researchers, put it so well, we only need to correct it approximately rather than exactly. And that is the absolute key. When you're sensing something, having a really good approximate answer is infinitely better than having no answer at all.
And that's the solution. It's a trade-off. You design the sensor from the very beginning to only worry about correcting some of the noise, the errors you expect to see. You might give up a tiny fraction of that maximum theoretical sensitivity, but what you gain in return is so much more important: robustness. The sensor can actually work in the messy, noisy, real world.
So what does all this really mean? It means the road to a practical quantum future isn't about chasing some impossible idea of perfection. It's about being smart and realizing that sometimes good enough is the new perfect.
It really just comes down to this simple trade-off. That perfect sensor in a lab, sure, it has maximum sensitivity, but it's fragile and almost impossible to actually use. This new meeting halfway sensor still has incredibly high sensitivity, but, and this is the big one, it's robust, it's practical, it's something we can actually build and use. So let's just recap the journey here. We saw how entanglement can create these amazing super sensors. We met their number one enemy, all that environmental noise, but the big takeaway is this clever new idea, this good enough error correction, that makes these powerful tools tough, practical, and finally ready to leave the lab. This breakthrough is huge. It really brings us to the edge of a new era, and it leaves us with a really exciting question to chew on. Now that we have a real path to building them, what will we discover first with these new quantum eyes and ears?